Lord, thanks. I'll begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray you be with us today. Help us to glorify you in what we do. In your name I pray, Lord Jesus. Amen. So you guys have any questions about any particular homework problems or anything? So the homework hard?
I have a question.
Mm-hmm.
The quiz 11, did you guys go over that yesterday?
No, I posted the solution to it though. So the solution's posted in Blackboard. You can look at it there.
For the second question, I didn't really understand how you got like the balance for t. Would you be able to do that?
I don't remember the second question off the top of my head, but if you remind me what it was, I could. Is any other questions about the homework while he's looking for that? No? Ooh. I'm busy all of a sudden.
Find the counterclockwise parameterization of this circle.
Oh, yeah. Okay. Yeah. So the problem was to find parameterization of x squared plus y squared equals to 4 given counterclockwise orientation and y is greater than or equal to x. So let's see here. So that's a circle, right? Roughly speaking. And what's y greater than or equal to x? I mean, the radius is 2, right? Y equals to x, we know what that is, right? That's no one has trouble with that, right? That's just a line y equals x, right? Now, if you say y is greater than or equal to x, what side of the line are you on? Below? Tell you what, let's pick a point. Minus 8, 7, right? What do we got? So x equals minus 8, right? Is 7 greater than or equal to minus 8? On the other hand, if you pick any point down here, say 8 minus 7, right? Then you'd have what? You'd have minus 7. Compare that. Is that greater than or equal to 8? So false, right? True. So in other words, this inequality puts you in this upper half plane. Right? That's where y is greater than or equal to x over here. So, but yeah, I know it's 50-50, right? I mean, am I right? So you know you're on one side of the line or the other. The question is which side. But once you realize that, then you realize this is thrown out over here, right? This is out. And we're just looking to parameterize this part of the circle. Right? Now the standard formulas that I presented you guys would be that we set x equals to 2 cosine theta, t. It is theta, and y is equal to 2 sine t for some range of parameters, right? I mean, we've been talking about polar coordinates lately, so you really could interpret the parameter as the polar angle in my parameterization, right? So geometrically, all you got to do is figure out what's the standard angle, you know, here, say theta 1, and what's the standard angle over here, theta 2, right? So I think it's geometrically clear that theta 1 is pi over 4, and theta 2 is 5 pi over 4. Because this is the line y equals x, which is pi over 4 below the negative x-axis. So pi plus pi over 4, 5 pi over 4. And so in summary, the parameterization is this r of t equals to 2 cosine t, 2 sine t, for t an element of pi over 4 to 5 pi over 4. I mean, that's a good answer. You could, you could do further here. I mean, what we're looking at is R is a mapping. What's the domain of it? The domain is pi over 4 to 5 pi over 4, right? And it's a mapping into R2. The image of this parameterization is exactly this red curve right here. So that's just, language. Language. I can't spell today. It's here. I spell language. A-G. There we go. All right. Of course, you could also go with the scalar parametric equations, right? So scalar parametric equations look like x equals to 2 cosine. What'd I do? Oh, I did? Seems like it should be AU. Here, I'll tell you what, terminology there. I think I'm good on that. There you go. I think today's the day I'm not misspelling terminology, so we'll stick with that one. So 2 sine t, and again, we've got pi over 4 less than or equal to t less than or equal to 5 pi over 4. This is another way of writing the answer. This is the scalar form of the answer. This is the vector form of the answer. Should be understood that these are describing the same function, which technically is a function from the reals to R2. Anyway, that's how you do it. So most of the question is just making this picture at the start and understanding what that inequality means to you. Yeah.
So is there ever a situation in which you wouldn't, even after drawing the picture, like you would have to calculate theta rather than just looking at it and knowing that, in this case, theta is pi over 4?
Yeah, I mean, there's always trigonometry. It's possible. If the line was y equals 2x, then I had to actually get a calculator out. Yeah. But yeah, I mean, it's certainly possible that if the problem's a little bit different, then you actually have to do a calculation to figure out the angle. I was trying to be nice to you guys, and make it so that you could just eyeball it. But
Would you be able to do an example like we're talking about right now?
sure, I mean, if I make it 2x, everything else but the same, but put a 2x here, then theta 1 try to eliminate all the static here. All right, so if I had 2x instead of x, then I know that the tangent of theta is y over x, right? But that's y equals 2x, so that would be 2x over x, otherwise known as 2. So theta 1 would be the inverse tangent of 2, right? Whatever that is. here. In degrees, we get 63.43 degrees, approximately. And then, of course, my picture is now misleading, but I mean, I'm saying it's 2x, so fine. If you want me to adjust my picture, I guess I should do this, right? So with this modified problem, right, it's pretty clear we've got theta 1 from 63.43 degrees, right? And here's your theta 2. Now, do I need to do further calculation with a calculator to get theta 2, though? I see. Yeah, I do not, right? There's 180 degrees from here to here, isn't there? So I just add 180, right? Theta 2 is 243.43 degrees approximately. Now, of course, to be a, I would put this over here to be safe. Inverse tangent of 2 pi plus inverse tangent of 2 for this problem there. Now I'm giving it in terms of radians. I mean, I really should write my answer in terms of radians. I'm sorry. I mean, maybe I should put these in like parenthetical comment or something, the degrees. Because we're using radians when I write 2 cosine t and 2 sine t, right? I mean, if you put 63.43 in for t, you'd be wrong, right? Because that's cosine and radians that we're using. You could say, I'm going to use cosine in degrees. Well, fine. If you're going to do that, then you better take a parameter range of about 63.43 to 243.43. I just was trying to make my new problem align with the old one. So if I'm going to do that, I should probably stick with radians, right? That's all. Okay, so the next topic that we have to talk about is basically just further applications of polar coordinates. So here's an example. If we have r as a function of time is equal to t, and theta as a function of time is equal to, let's say, 2t, for 0 less than or equal to t less than or equal to 1, then what is the arc length of this curve of the path, let's say? So how would you figure that out? What do we know how to calculate arc lengths of at the moment? Given our current technology, here's how I'd have to do this. So I can find x of t and y of t. How can I do that? What's the corresponding Cartesian parameterization? See, I've given you r as a function of time and theta as a function of time. So how do I find x and y? X is r cosine theta, y is r sine theta, right? So just x of t should be equal to, what we got? We got t times the cosine of 2t And we've got y as a function of time being, looks like t times the sine of 2t. Right? So, I mean, for lack of a better idea, that's what I would start with. So then, in order to calculate, so there you go, that's the corresponding Cartesian parameterization of this curve, right? So then what? To calculate the arc length, we need to calculate what's dx dt, what's dy dt. Well, dx dt here is what? By the chain rule, right? dy dt is sine 2t plus 2t cosine 2t by the product rule and chain rule. I square these, right? So what's dx dt squared plus dy dt squared? Something nice happens, right? The cross terms in these squares cancel out, right? And you just end up with like cosine squared 2t plus sine squared 2t plus 4t squared sine squared 2t plus cosine squared 2t. The other terms, the cross terms, if you will, those cancel out because you get plus 2 and you get minus 2 from the other, right? Well, plus 4 and minus 4, right? So then what? Well, cosine squared plus sine squared is 1, right? So what do we got? We've got 1 plus 4t squared, right? Simplifying sine squared plus cosine squared to be 1. And what we're looking at right here, this is equal to v squared, where v is equal to ds dt, right? It's the speed. So how do we calculate the arc length? We integrate that, right? S is equal to the integral of ds, which is, by the way, the integral from, in our case, time 0 to time 1 of v dt, which, by the way, is the integral from 0 to 1 of the square root of 1 plus 4t squared dt. And so this is an integral we can do, right? It's not pleasant, but we can do it. We let, basically we're looking at this as being 1 plus sinh squared theta, or whatever variable you want to use. I'll use theta. No, I'll use theta. Theta's already been used in this problem in a different sense. Let's say sinh squared beta. So 1 plus sinh squared beta is equal to cosh. I'm an idiot. Let's try this again. 1 minus sinh squared beta, right, is equal to cosh squared beta. So that suggests to me then that I'm still wrong. Let's try this again. Cosh squared minus sinh squared, right, is 1. So from this, I get that 1 plus sinh squared beta is equal to what? Cosh squared beta, right? So this identity makes me think of comparing 1 plus 4t squared to that, right? So that suggests to me that I make a I want to make 4t squared become sinh squared beta. So that means let 2t equal to sinh beta. All right, so with that substitution, we have the integral from 0 to the inverse hyperbolic sine of, let me think about this for a second here. If t equals to 1, then 2 is equal to sinh beta. So therefore beta is the inverse hyperbolic sine of 2. So inverse hyperbolic sine of 2 is the transformed upper bound. This stuff becomes cosh beta, and my dt is 1/2 cosh beta d beta. So I get a 1/2 out front, and then another cosh beta d beta. So that's a 1/4 integration from 0 to inverse hyperbolic sine of 2 of 1 plus the cosh of 2 beta d beta. Sorry, I got out of the way. I was just curious. You have a question?
I was lost when you put 2t equals sinh beta.
Oh, okay. So the motivation for that is I know that I either make a trig substitution or a hyperbolic substitution to get rid of a radical. I remember that trig substitution leads to secant cubed here, which is unpleasant. So we're going to go trig. We're going to go hyperbolic. So the way to think about hyperbolic is I want to recognize this as 1 plus cosh squared. Basically, it's going to be 1 plus sinh squared. Because I know 1 plus sinh squared is equal to cosh squared, which will make the square root go away. Because the square root of something squared is just the thing again. So I basically, that leads me to make this 4t squared match up with my sinh squared beta, which is what forced on me the substitution 2t equals to sinh beta. Once I make this substitution, then that makes this square root just become this. And the dt, by differentiation, is 1/2 cosh beta d beta. This half I pulled out front. That's from this. And then I had to change the bounds as well. Right, 0 goes to 0. 1 gives me 2 equals to sinh beta, so beta is inverse hyperbolic sine of 2. Cosh squared is 1/2 of 1 plus cosh 2 beta. I pulled the half out to give me a fourth, because a half times a half is a fourth. And now I integrate. But before I integrate, does that make more sense? I mean, it's been a while since we did these, but so anyway, what we get is 1/4 inverse hyperbolic sine of 2 plus 1/2 of the sinh of 2 times the inverse hyperbolic sine of 2. And that could be simplified a little bit more, but I'm going to leave it like that. Okay? So there you go. So maybe it's worth our effort to try to derive and see if there's some kind of, like, this is fine. I mean, this is a method, right? If you're given a curve, parameterized curve in terms of polar coordinates, right? If you're given r as a function of t and theta as a function of t, which is a polar parametric description, right? See, that's what I started here. This is a polar this is parameterized via polar coordinates, right? Maybe there's some kind of nice formula we can find just to find an arc length integral directly in terms of that r and theta without having to go through this x and y stuff, you know? Maybe there's something nice we can derive, right? Because this sine squared plus cosine squared, maybe that happens in general, and maybe we can just address it once and for all. So let's try to work through it in the slightly more abstract case. So what we're going to do is try to redo this problem, but for an arbitrary parameterization, and see what happens. So my starting point is I'm going to assume I have r as a function of time, theta is a function of time. So I've got some parameterized polar curve. So I've got r is equal to, you know, let's say r of t, and theta is equal to some function of time as well, for t1 less than or equal to t less than or equal to t2, all right? Let's go through this calculation in a little bit more generality. So this means that we're going to have x equals to what? R cosine theta, and we got y is equal to r sine theta, right? We can still do that. When we differentiate these, what do we have to do? They have r and theta functions of time, right? I mean, I made it explicit over there. The function of time was t and 2t. But just let's be a little bit more abstract. Let's just say arbitrary functions of time, okay? So to differentiate dx dt, what do we get? We get cosine theta, right, times dr dt, minus r sine theta d theta dt, by the chain rule and by the product rule. Likewise, dy dt is sine theta dr dt plus r cosine theta d theta dt. Okay? I actually prefer the following language for this. So we have x dot equals to cosine theta r dot minus r sine theta theta dot, and y dot is equal to sine theta r dot plus r cosine theta theta dot. This is the so-called, you know, Newton's. This is Newton's notation, which is just that, like, d theta dt we can denote by theta dot, etc. It's a nice compact notation. It's a standard notation, especially used in physics. Anyway, so what happens when you look at x dot squared plus y dot squared? You get what? You get we get cosine squared theta plus sine squared theta, both with an r dot squared. The cross terms cancel, right? When you square these, on the one you get a minus 2 r dot theta dot sine theta cosine theta. On the other one, you get a plus 2 r dot sine theta cosine theta theta dot. So the cross terms are equal and opposite in sign, they cancel. And it's just the squared terms that survive. You get a cosine squared plus sine squared r dot squared. And from the last one, you get a r squared theta dot squared times sine squared theta plus cosine squared theta. All right? This simplifies, obviously. And here you go. X dot squared plus y dot squared is equal to r dot squared plus r squared theta dot squared. So here we go. This is the speed squared. So what you're looking at here is something actually kind of interesting, believe it or not. This is the speed squared in Cartesians, right? Coordinates. And what are we looking at here? This is the square of the speed in polar coordinates, right? So, that's pretty nice because then from this, right, we get a formula for the arc length in polar coordinates. What is that formula? We can integrate from t1 to t2 the square root of r dot squared plus r squared theta dot squared with respect to time. And that will give me the arc length as calculated from a curve parameterized in polar coordinates. The parametric polar, like we had over there. This also has interesting physical significance. So if you study kinetic energy in physics, have you guys studied kinetic? Show of hands, who's in physics 1 right now, 231? Okay, so have you guys talked about angular momentum yet? You in the rotational physics yet? Circular motion? Just doing it right now. Excellent. So what you're looking at here, this piece is the radial component of the velocity squared, and this piece right here is the tangential part. This is vt squared, the tangential part of the velocity squared. But the tangential part of the velocity squared can also be written as the radius squared times omega squared. In other words, the tangential velocity is equal to r omega. This is the r omega squared term, and this here is the part with the radius changing. A lot of the problems you work in circular motion, you work along a circle where the radial velocity is fixed because you're at fixed radius. And so all of the interesting stuff is happening with the tangential velocity, which either speeds up or slows down according to how the angular velocity omega, the rate of change of the radians is increasing or slowing. But the relation between the Cartesian velocity and the polar velocity is really just nothing more than chain rule and algebra. So anyway, pragmatically speaking for this course, this formula is very nice because it allows us to not recreate this proof as we just did here, right? This is just the proof for this specific example. Now, it probably doesn't take away the pain. It probably doesn't take away the pain. This is probably still waiting for us, whether we like it or not. Let's try this example again, but now with our new toy. See how it changes. So instead of switching to Cartesian coordinates, let's just calculate directly with our new formula. So we have s is equal to the integral from 0 to 1 of the square root. Let's see here. R equals to t, theta equals to 2t. So that makes r dot equals to 1 and theta dot equals to 2. So we get 1 squared plus r squared. But what is r? T, so t squared. Theta dot squared is 4 dt. Okay, so, there's a certain badness in this problem that cannot be avoided. But there it is. Look at another example. See if I can make this one turn out nicer. Debatable. Unless, of course, you guys have a question about the homework. suppose we have, if you have r of t equals to e to the t, and we have theta of t equal to, how about sinh of t for 0 less than or equal to t less than or equal to natural log of 2. Let's find the arc length of that curve. Okay, so here we go. We integrate from 0 to log 2, square root. Let's see here. So our r dot is e to the t, right? And our theta dot, oh, I chose poorly. That's supposed to be cosh t. My apologies. Cosh t. Cosh t. Cosh t. Cosh t. Cosh. Important. Cosh t. So theta dot is sinh t. Right? So when I look at r dot squared, I've got e to the t squared, and then r squared is e to the t squared, right? And then theta dot squared is sinh squared t, right? So I'm just, this is, that again is r squared plus r squared theta dot squared, right? I'm sorry, other way around. R dot squared. I'm an idiot. Although this problem is somewhat forgiving if you confuse r and r dot, right? Like confusing r and r dot won't make you wrong here. They're equal. You guys are subdued. Is it because of all your fallen brethren? Is it all the people that you've lost, that you see all the empty chairs around you? Is it sobering? It's not my goal. I really want all of you guys to stay here till the end. I mean, I told them I will replace the final exam grade. Like, you need this class to graduate anyway. Why not try this semester? It's not like if you wait to another semester, you're going to have a substantially easier course. It's not the case. Calculus 2 is Calculus 2. There's an insurmountable difficulty here. I mean, it's surmountable. Excuse me. There is a difficulty in this course which is consequential. I mean, it requires work. There is no getting around this course except the work. It was the same for me. This is one of the hardest courses I ever took. It's just the nature of the topics in this course. They're tough, and there's a lot of them. And when you think you're done, there's another one right around the corner waiting to get you. Right? It's like one after, but anyway. But there is hope. Just keep at it. You'll get it one step at a time. But you got to ask questions if you're lost. And you guys are not asking questions, which makes me worry. Because you didn't have any questions before the last test. And then what happened?
You all aced it.
You all aced it. Yes, very good. Nope, still awake. Okay. Here. E to the, okay, so integration, you all aced it. It's funny. E to the t. I wanted to see if this was a dream or, what the deal was. Anyway, so as you can see, I have manufactured this example as to permit the factoring out of e to the t. Yay. And also so that 1 plus sinh squared becomes cosh squared. So what we're actually looking at here is something rather innocuous. E to the t cosh t dt, also known as the integral from 0 to, and here you got to go back to definitions, right? So you got like 1/2 e to the 2t plus 1/2. Right, to get from here to here, that's because cosh t is what? So when I multiply that by e to the t, I get e to the 2t from the first term. And then e to the t and e to the minus t, they obliterate each other in a flash of light and just become one, right? So this is the natural enemy of that. Just gives you half when you multiply. And now you can integrate. So you got yourself a 1/4 e to the 2t plus t over 2. You got to evaluate that thing from 0 to log 2 and see what happens. Looks like we got a 1/4 e to the 2 log 2 plus log 2 over 2 minus 1/4 e to the 0, which is just 1. Let's see here. We can clean this up a little bit. What's e to the 2 log 2? This is a very weird way of writing 4. So this is actually equal to 3/4 plus 1/2 log 2. It's kind of a quirky thing. On the face of it, this looks more complicated than my first example, but when you actually work it out, it's way easier. It's a funny thing. So I think the things I haven't covered yet in this chapter are mostly things like moments of inertia and other things you'll find in the homework. You really should try to work those problems so we can talk about them, right? You know, there are some running examples in this book, right? Like calculate the moment of inertia of various solids, find the center of mass, things like that, right? And those are some kind of standard problems, but you can ask them in our current context, right? You could do stuff like if you have a solid laminate constant density, so I usually use sigma for that, dm dA, the mass per unit area. And suppose that this is a half circle, radius r. You could say find the center of mass. So to do that, you have to do what? Well, I suppose you have to find out what the formulas are. But basically, x bar, geometrically, you can see that it's, you can see here from the symmetry of the problem, it has to be something like here, right? So we use x bar, y bar, that's the notation for it. We want to find that point. So here's the formulas for it. X bar is equal to 1 over the mass times the integration of x dm over the region. We call the region R. And y bar is equal to 1 over the mass times the integration of y dm over the region. Now what's m? What's the mass? See, dm is sigma dA, right? So the mass, the total mass, is just the integration of sigma dA over the region. Now, since I said that it has constant density, we can do that calculation without a lot more work, right? What's the area? I mean, we can pull the sigma out because sigma is constant, right? If sigma is constant, we can pull it out of the integral. And what's the integration of dA over the region? It's just the area, all right? So that is just sigma times pi r squared over 2, right? Then the question is, how do you calculate these things, right? In the old Cartesian way of thinking, well, first of all, we don't calculate the first one, right? We use thinking. We say, it's geometrically obvious that x bar is equal to 0, right? So we don't have to calculate anything there if we're willing to embrace symmetry arguments. I hope you're willing to embrace symmetry arguments. I certainly am, right? This, on the other hand, we need something else, all right? So, so the dm is sigma dA, which we could write as sigma r dr d theta, basically. Well, I'll tell you what, let me leave it as dA, sigma dA. Okay, so in polar coordinates, what's this look like? What is this region in polar coordinates? You draw the line out here. What's the inner radius? 0. What's the outer radius? R, right? This is a very boring polar region, isn't it? So in polar coordinates, I would integrate from 0 to pi. This y, what is y? Let's see here, what's y? Yeah, r, I just heard it. Have courage, speak up. R sine theta, yes? The dm, right, is sigma dA. Now this dA, we figured out how we integrate dA in polar coordinates. We figured that out before, right? It was 1/2 rho squared d theta, right? We still do that here. So I do 1/2 r squared d theta. And let's see here. So I got a sigma. And this sigma over, oh man. Oh. Nah. I'll have to go. Nah. I'm not sure about something here. Oh man, I'm out of time. What? Was my phone buzzing at me? The thing that's troubling me here, guys, is this R. I don't think I should just make that capital R. Oh. You're... Just a second. I have gotten overambitious. Oh, now I remember why I can't do this. Oh, this hurts. Oh, on page 495. Oh, this is painful. Look. Well, oh my goodness. Oh, that's weird. So basically page 495 says what you have to do is 495 says that the area times y bar is equal to 1/3 the integral of rho cubed sine theta d theta. There's no derivation of this. This just appears in exercise, well, exercise 33 is for you to show this. Yeah. I'm sorry. This is what I have to use. No, I can't. I was hoping I could just piece things together here, but I forgot about this issue. I usually do things from a Calc 3 perspective. In Calc 3, we just change dA to r dr d theta, and we have a double integral here, and it's not an issue. This formula in exercise 33 is really a weird thing. There's some weird problems in this book in calculus too. This is one of them. Anyway, I'm sorry guys. I have wasted your time. You have to integrate sine cubed in order to calculate the centroid here in the polar coordinate way. So sorry.